the when Philip challenged me to come here, I thought a bit about what I could talk with you regarding what I do in my daily life, let's say. And I actually thought about like when I was at the group, I only did the master thesis, so I was like for 8 months, 9 months, 10 months there. From things that I actually didn't know at all at the time, and now I know from what I've been doing the past 5, 6 years, which is actually putting things into production systems. So like actually after doing the research and training models, how can we turn those models and all the algorithms into something like that runs in production for real systems, real world and real data. So uh, before that, just for you to understand what I've been doing since I left university and like how I came here to this point where I can actually talk a bit, not a lot, but a bit about this topic. So I studied bioengineering at Philp. I specialized in biomedical engineering and focused really early on AI, coding, so a bit of both. I actually did some no, actually a lot of subjects with informatics, so computer science. And I actually ended up doing the master's thesis in the group. At that time, it was with Professor João and Ana Filipa, and the topic was detecting fake, like fingerprint counterfeits, more focused on unseen attacks, so things that were not seen in the train, trying to detect them in the prediction stage. I did actually a lot of things from more traditional machine learning to computer vision. Actually tested a lot GANs at the time to do this, a bit of domain adaptation. So like a ton of things. And I actually at the time really thought about the topic of then seeing things running in production. So that's why I made the decision to go to the industry. I started working in data science in like a big company, IoT focused. It's like it was huge, more like it was focused on in the United States, so a completely different mindset. I worked with a ton, like a lot of data, a lot of structured data, tabular data, time series. I started working a lot with, or I gained a lot of knowledge at the time, trying to manipulate those big amounts of data. Then I moved to a startup, and I started with a startup world, which I've been since this moment. This one I love is a med tech company. Actually, I did a lot of research here, a lot of deep learning, a bit of computer vision, but mostly like one dimensional deep learning. It was focused on like blood samples or human-based samples to detect things in the samples. But it was in NLO that I actually started to experiment a lot with making the models into production systems. We actually had to do real demos in specific cases with real people, like people there watching us taking samples. Then the device would analyze the samples, and in real time we should see the results in a UI in a website that we built in like one day. So we needed to. None of us at the team at the time knew how to actually build things in production, so we need to learn. We need to learn everything from scratch, and it was like an amazing, like learning. Everyone trying to do different things and try to do like to find the best way to do that. And actually gain a lot of like I liked a lot the process. I decided to to explore more that area of making things into production systems. And after like 2, 3 years, I don't remember the time I was there. I started doing some competitions in data science, more focused on sustainability. So nothing like nothing related to what I've been doing. And I met my current company, which is Enlitia, like Philippe said, and Enlitia started as a machine learning engineer. So now actually focused on putting things into production. And I've been there for almost 2 years now, and now I'm leading both the machine learning engineering and data engineering team. So not only putting things that data science does into our systems, so putting models into production, but actually also managing the part of data pipelines and databases and getting data from the clients and from the sources so the models can actually do things. Apart from that, of course, I need to mention this. I actually co-founded a company 1 year ago, I think. At the beginning, it was nothing to do with technology. Now it's starting to be. We started with like a simple natural pet food company, and now, but our vision was always related to technology, and now we are starting to do that. So we are creating an algorithm that creates, let's say, personalized toppings for pets, focus on dogs now. So it's not AI, it's more, let's say, analytics, algorithms, optimization algorithms. So my experience with machine learning into production is more, of course, from the last 3 years, mostly at Enlitia, and my experience at I love. And I will focus on that with different examples throughout the presentation. So at Enlitia, focus on that. We actually started as a bit of a consulting company. Let's say Enlitia is not, it's a startup, but also a spin-off from another company, an older company. It actually started at UNESCO in the part of the energy department of UNESCO. And the company started as like 100% consulting, doing tailor-made projects for the energy field, more focused on renewable energy. But then 2, 3 years ago, the company decided to focus on creating a new product, a standardized product that comprised like all the knowledge and the algorithms that we've been building for the different clients into one single platform that like joins everything, and it's standard, and we can actually onboard much more clients and go international without scaling considerably the team. So we started doing that, and I was actually hired to start it, or actually to make it into a real thing. What we can see here is basically one of the snapshots of the platform. So the focus is basically monitoring the different assets. Assets in renewable energy are the wind turbines and solar panels and etc. I think I will say that the term assets a lot for the next 30 minutes. So the goal is to monitor the assets, detect issues, understand what will the behavior in the near future. Everything in the same platform, the clients can see the entire portfolio and the entire production in one thing, and it's basically that. We have a lot of different algorithms here. We have things about performance, like detecting performance issues in the turbines, like if they are producing less than they are expected to do. We have health algorithms like failure detection, predictive maintenance, so try to understand if that specific turbine can fail due to a specific component in the next days and warn the client about it. We have predictive algorithms focused on forecasting, so a lot of time series here. Actually, 9% of the data we work with is time series data. A lot of forecasting, trying to understand what will be the state of the market, the energy market in the next few days, the state of the production of energy in the different wind farms and solar farms for the next days, and so on. And everything is very well tied with the concept of data quality. I always mention data quality because in the energy field, the clients, it's a not very well developed field in terms of technology, so they really need to understand what we are saying, and we need to be very transparent in terms of like explaining the outputs of the models, and data quality for them is very important because they really need to know why they if they can trust, let's say, in the data and in the outputs of the models. If the data quality is not very good, probably they will not look at the insights generated from the models and from the data. They will ignore it and wait for the data to be good. So the concept of data quality is very important. And what we are doing with this specific product is we are not creating just a single platform with individual algorithms working with like specific predictions. We are building what we define as an algorithm ecosystem, because then the different outputs of the different algorithms are basically joined with more algorithms, so it's a bit of an ensemble, everything working together, and it's like a mixture of things. And in the end, they have like very simple, quite simple insights that like are the end line of a very more complex process of a lot of data sources and a lot of models towards that specific simple insights, because again they need to have simple things so they can make easier decisions. So this is overall what Enlitia does, and just for you to understand, one of our clients has like the last time I saw near 3,000 turbines and hundreds of solar panels. So some of the models we train and we develop are for the entire portfolio. Some of the models are for example, wind farms. Wind farms are like 20 turbines. But some models are actually done per turbine because they are very particular in some specific cases, like analyzing specific components. So we need to make models per turbine sometimes. So imagine that's like the problem, the complexity of putting one model that was trained for a couple of turbines during development stage and then need to run for 3,000. And it's actually one of the big issues and challenges we have at Enlitia. Completely related to the topic of putting models into production. So the data science team does models, machine learning models to predict something about a solar panel, and the data set is basically this very beautiful, perfect single solar panel with the perfect data set. Everything is cleaned and perfect, no missing data. Or if it has the missing data, they can just remove the missing values. And then in the end, we have to put it to run for this farm. So yeah, it's not easy, and that's why we struggle every day in the part of machine learning, engineering, and data engineering. I actually tried to think about the most typical errors or issues that we find during this process. Okay, so this is a very fluid process. Okay, we have actually two different teams. We have one data science team and one machine learning engineering team. Mine is the learning one, but we actually work together all day and every day. We basically have different goals, but we work together, and we actually have people from both teams that do both things, like end-to-end projects. And I try to think like the top 4 or 5, I don't remember the number, of problems I actually I've been finding in the last years. So we can start this conversation. And the first one I remember was the what I called the feature disappeared. So like I wrote there, turns out the user favorite color last Thursday was only in the training set. This is actually very common to happen. Okay, sometimes we are training things with data that the client sent us from 2010. And at that time, they were collecting a specific variable for a specific sensor in the turbine. And then the real-time data, the data we have now for prediction, doesn't have that specific value, the specific sensor. So yeah, if the model was trained and we gave a lot of importance to that specific feature, nothing works. Other thing, the data drift, probably you know the term and what happens. It's actually very common in the energy field. Solar panels and also wind turbines, they have a sort of degradation. So after some time, they start to degrade, and you can actually see differences in the data from year to year. So imagine if we have the data set of 2010 for a solar panel, and we create a model to predict the production, for example, for the next days. In the end, we'll have, if we do the predictions for today, the model will say that we should be producing more than we've actually been producing. And that's not because the model is wrong, that's not because the data is wrong, it's just because we have a drift in the data, it changed, the behavior of the asset changed. We have then what I called it sees dogs everywhere. So like if we train a model to predict types of cats, and then we input a dog, it starts to predict the dog as a cat, or it tries to predict the dog as a cat. And it happens also in the energy field. So let's imagine a model about soiling. Soiling in solar panels, it's like dust accumulation, which of course decreases the performance, it decreases the production of energy. If I train a model to detect soiling in a solar panel with data from like the UK, where it rains a lot, not that much of a dust, not that much of an issue related to soiling. And then I put that trained model into production for a solar farm in Morocco. We tried that, it doesn't work. Trust me. So again, the domain here is very important. We need to always make sure about the domain where we are training things and putting things into production. And then the most common one, what we call it worked on my machine, or it works in my machine, where yeah, when we are training things, everything is perfect, 100% accuracy, runs very smoothly, and then yeah, we need to put it to run to like 30,000 turbines, and they are in a completely different geography, and it's all wrong. So these are all things that I've been learning, and we have been learning as a team for the past 3 years. Now we are a bit better on that, but still a challenge every day. And the thing we need to do to actually tackle these issues is to be very mindful about the process of putting something, machine learning model into production. I simplified. I have the next slide as the complete, more complex version of this process, but I simplified into 4 main steps. The last one is also important. It's not a step, but it's also very important. The restart button. So the part of data, okay, we have, after the data being collected, I will remove the data collection from here. We have, of course, the initial exploration of data, feature engineering, feature selection. You all are experts on that, more than me probably. And then, of course, we start to build a model. At this time, it's very common to have very good accuracy, because if we don't have in mind the problems I mentioned before, it will not happen in production. So at this moment, everyone is very comfortable about the results, but everyone knows that the battles are coming, and then we start to do the part of production code. It is actually very important, and at Enlitia, most of the times, the separation between data science and machine learning engineering happens here. So the training is more of a data science thing, and then the production code goes to the machine learning engineers. But again, this is not like very strict. We have people that do everything. So the production code is actually more of a software engineering challenge here. So it's about making the code readable, making the code very standard in terms of company-wise methods. So we have different projects with different clients, but everything needs to be more or less standardized so we can have support, because again, we have a lot of support in the clients in real time. So we need to have everything more or less standard in terms of different projects. We have to test the code. We have to test the code in terms of software, but also in terms of speed, in terms of resource consumption, everything. And at this moment, Jupyter notebooks die, of course, and we start doing real coding with scripting. And then until this point, everything is Python, and we use 99% of Python. Some things are not Python, but mostly they are. And then we have the part of monitoring. Okay, very important. A model is not really in production if we are not looking at it. And yeah, we need to look for accuracy. We need to look at the data. We need to look at the input data and then the output data of the models to understand if there are issues, like if the model has issues in terms of output. Probably the input is a very probable case. We need to look at resource consumption. So this is like I said, the monitoring hell, because we ourselves are looking at the dashboards every day, but we have also the client looking at it every day, and the client have different issues that we have. We have the issues of like it's taking too long, or the resources are too high, and then the client are just want to understand why the 5 is not a 4, right? So we need to battle between both. And then we have the part of restart, which is the CI/CD. CI/CD is continuous improvement, continuous deployment. So as typical software has the continuous improvement and continuous deployment process, machine learning also has. Actually, there are people that call it continuous training, continuous deployment. Not 100% true, because we don't need necessarily to always train the models every time we do some changes. But yeah, there is of course continuous improvement and continuous deployment, which is very important that we made from scratch well. Otherwise, it will be a mess, because if we need to change things because that feature will stop to be used, or that feature will disappear from the data. We need to be able to have a simple and efficient process to do the changes without breaking everything in production, right? So overall, it's very simplified. This is the process. Like I said, there's the complete version of the process here. I can go very quickly, just enumerate the parts. We can start with the plan, of course, of the project. We formulate the process it's the same in terms of it's the same people here planning and formulating the issues. The planning is more functional with the clients, formulating is more with the technical team, but yeah, it's more or less the same thing. Then we collect the data. It's a part of data engineering, so you will have different teams here working together. Of course, we have the part of transforming the data, saving the data in whatever place. It can be in files, it can be in databases. And then when everything is validated, we start to explore. Here, the data science and machine learning team enters. We train the models, evaluate the models, and then the part of developing code starts. Then build like coding the project into something that can go to production. We build the system itself, we test, and then it releases. We deploy in whatever place it needs to be deployed. I will talk about that later. And then everything needs to be monitored. And if anything is wrong, we start to plan again, and the cycle continues. Okay, so more or less this is the daily life of the machine learning engineer, but it's in the middle because a machine learning engineer knows how to talk with the research data scientist, knows how to talk with the data engineer, knows how to talk with the DevOps team, and with software engineers. So yeah, we are basically in the middle of the different teams. One thing that I actually noticed when I changed from pure data science to what I'm doing now, and I started as a pure data scientist, was the huge difference between the number of tools I used at the time and the number of tools I use now. So at the time when doing 100% data science, I basically used a bit of like VS Code sometimes, mostly Jupyter Notebooks, databases sometimes. So it was 2, 3 technologies in my daily life, most of it. Now I have 6, 7, 8, I don't know. And each step of the process can have 2 or 3 different technologies. It depends on the client also. We are not the only decision makers in the technology we use. And I try to compile like 5 or 6 that are most common, not the actual technology. I have some examples, but the concept of the technology, the entity that is technology. I try to do some cool analogies here. It's true that I did a lot of this presentation with ChatGPT, talking with me about ideas to do analogies. I really like analogies with ChatGPT. So first we have the WISE. Okay, the WISE is the model registry and the experiment tracking technology. Probably use that. I don't know. I've been using these since I was just doing research data science. MLflow is the most common one I've been using for the past years. It basically registers the different experiments of data science, and then we can register also the models there. So the models are saved there with versioning, with metrics, with artifacts, metadata, etc. So this is the one like stores every information about the models. Then we have what I call the assassin. The assassin is an API. This is not true for all cases, but some models actually need an interface, direct interface with someone, with a client, with an application. And the most common thing to do is to have an API that triggers the prediction and the training of the models. In Python, if we stick with Python, Fast API is the framework that is more common. But actually, at Enlitia, we are not using Fast API and Python for all the APIs. We are actually using different languages for this because they are more efficient than Python. Then we have what I call the blacksmith, which is Docker. Docker has been the center of everything the team has been doing for since I'm at Enlitia. Basically allows us to put things running everywhere at any time, and it works. It basically removes the problem of it was working on my machine. And basically, it's the center of all processes and the orchestration of processes. Then we have the strategist. Here, the technical name is the orchestrator. Okay, so when we have systems like the product that I was showing to you in the beginning, we need to be able to orchestrate the different predictions at different times, to have triggers, manual triggers. We have to have schedules of predictions, and there are a lot of technologies that do this. Prefect is the one we have been using more at the company, but there are a lot different all of them are quite good. So yeah, it's just a matter of choosing one and go on with it. But this is the center thing of a system. This with Docker, and I will explain this. I think it's the next slide, but the orchestrator and Docker are basically end-to-end in all systems. Then we have the Scout, which is Grafana is one of them, but it's basically the dashboard, the dashboarding technology. So for the monitoring part, very important. This is good not just for us, but also for the client, because we can do like dashboards for us with more specific and technical metrics, which we always do. And then we have like more simplistic dashboards for the client to see while they don't have a final UI to see the outputs of the models. And finally, you have the healer, which, like I said, the continuous improvement, continuous deployment step everything entity, which is very important because it allows us to clean issues, to debug, to like fix things without breaking everything that the client sees every day. So overall, this is the 6 different types of technologies that are more important. And I was mentioning the thing of it was working on my machine, and I mentioned that Docker is the technology that allows us to remove that problem. But then we have the other problem of it works on my container. This happens a lot. So although we use a lot of technologies and tools, the problem of it works on my container still happens, and the reason is because we still need to look a lot on the code, and the most big part of the process is not using the tools but actually developing the code. In the end, it all relates to the code. The technologies are just helpers to reach the goal of the final system. So now for you to see now for you to see how these would be actually related and work together in a real system, I thought about a simple example of one of our projects that has been working for some years now, and I tried to do like the entire pipeline process of a system in production. So it started, of course, with the model development and data exploration, feature engineering, and so on. We usually use Jupyter Notebook for this. It's easier to show things and to do this part of the job. Then nothing. And we start to do the production code. We usually pass to VS Code, of course, still in Python. I think everything here is in Python. And when the production code is ready, we'd like to do a lot of things in classes, put everything in functions, modulating the code into different in different scripts, so everything is readable and easy to maintain in production. And we use, of course, GitHub to manage all of these. We have very big project that we have like 2-3 people working at the same time there. So GitHub, huge. And very important at this moment. And then when the code is ready, we have the part of CI/CD, which in our case it's mostly done with GitHub Actions. Basically, they are specific sets of code that we program directly in GitHub, that when the code is ready, like when we push things to a specific branch in GitHub, the GitHub will run a pipeline, which is a GitHub action that builds a Docker container or does something else, runs some tests, whatever. And then in the case of a Docker container, it pushes the Docker container to a Docker registry. The Docker registry is basically a GitHub for Docker containers. So they are all there, Docker images, like they are all there, ready to be pulled and to run the code. So if I then, like after putting a code into GitHub and GitHub putting that code in the container into a Docker registry, I could go with my computer, pull the image, open the image, and run the container, and it will work and run the model or the process or whatever. Then these GitHub actions also communicate with Prefect. Okay, Prefect, like I said, is the orchestrator, is the technology that actually runs things. It decides when to run the specific prediction process for specific models and decides to manage the manual triggers and so on. And when Prefect needs to run some code, some prediction, it pulls the image from Docker and run it. Okay. And to run it, it needs to, of course, interact with the other technologies, like MLflow in the beginning, like I said in the beginning. So pull the machine learning models, the trained models, or or save the model if we are running a training process. And then we have, of course, databases, and we use mostly relational databases here with the data, like input data going into Prefect and Prefect saving the output data of the models into the database. And like I said, also, we can like wrap everything into an API that interacts directly with the database, but also with Prefect, so we can trigger manually trigger specific predictions or trainings of specific models. And overall, this is a use. I think this is the more standard thing we do at Enlitia when we have a new project. In the case of the product, it's a bit more complex. We use more like 3 of our technologies at the same time to orchestrate things because we need to manage a bigger load of data and bigger load of clients and models. So yep, that's it. I just to finish, and because I want to focus more on Q&A, I decided to think about some lessons I learned with the team. So not just me, with the team in the last years. And after this, I have some some topics that I didn't mention, but I can mention very quickly and very briefly for you to know, because there are things more deep about machine learning engineering that we can discuss about, and you can ask questions about it if you want. So, first one, premature optimization is your greatest enemy. It's very common for a data scientist to overcomplicate or do a very complex model to do a task, and then the model doesn't work in production because it's too heavy or because the data in production is not it's not the best data. So one thing that we need to be careful about here is to actually think about not always the MVP model, but the most I usually tend to say to the team the most satisfactory model we can get, that we feel good about it. Not the perfect one. We can think about the perfect one eventually in the future, but go and put in production the one that we feel good about it, but it's not the perfect. So don't try to be too deep in terms of optimization, because usually it breaks in production in the first time. Write code so future you can understand it, not future you, but also different people, of course. The part of creating and developing production code that I say before is very important, really. Mostly, of course, because of efficiency, but also because of readability and to help the maintenance of the code. Because yeah, we need to maintain and repair systems and models that have been running for 3 years now. So, and the people that developed the model are not here anymore, and we need to be able to support on that. So it's very important to actually write very clean code. That's why I said we have standards in the company that we define. So if we are doing a prediction, it should have more or less the structure, and we need to put more or less things in that structure so everyone can understand it, even though the inside of the prediction is very different because it's a different model. So this part is very important. Then a fun one: Friday deploys are brave or foolish, often both. Here is basically not just not to do deploys on Friday, but the conclusion is that we need to take time after deploying to actually look at things. It's very common in the industry to we have to do things very fast. Everyone is the pressure is big from every stakeholders, and we need to always make sure to take some time, like the morning before, the morning after, or the day after deploying a model, to look at it, do some quick plots, some data analysis, just to be sure everything is working as very well. Because usually when we deploy things, the clients don't look at it immediately. They look like after 1 week, for example. And if we just deploy a model, leave it like that, and then 1 week after the client starts to complain about some issues, it's even more difficult to then fix everything and do everything. And of course, we don't want the clients to be our QA engineers. Then if it's not monitored, I said this one in the beginning, if it's not monitored, it's not the production. It's more or less the same as the Friday one. So we need to monitor everything, and to be sure that we have a monitoring task after deploying the model. And then alerts are like horoscopes, fun to read, but mostly ignored. It's very common also now for the machine learning engineers to put logs and everything, alarms and everything. If this doesn't run, I want to be alerted. I want to receive an email or a message in Teams, and then in the end we end up with 1,000 messages per day. It happened actually, and we just block that sender or that specific channel in Teams, which is not good. So we need to be very smart in terms of creating logs and alerts, because we only need to know the really important things and not like everything that happens. Because sometimes, yeah, there's a failure in the code, which is okay. We need to understand the reason behind, but it's okay to happen once. Maybe it's not okay to happen 10 times, but yeah, we need to be very strict about what we want to see in terms of logging alarms. And yeah, finally, some things that I didn't mention, I will mention now. We can talk a bit about this afterwards if you want, but more like complex things that we usually do in this area. So doing tests in production, apart from testing things in development, there are some cool ways to actually, when developing and releasing a new model, try to see like comparing it with the previous one, and there are some cool ways of doing that. There are some examples. We have things, of course, about explainability and dashboarding. The explainability is very important. The data quality thing is our biggest strategy here. So we focus as much on data quality algorithms as we do in predictive algorithms, and that's our way of explainability. But yeah, we could have different strategies. The difference between batch processing and stream processing, at Elite we do a bit of both. Batch processing is getting things in batches, like like the name says. So accumulating data for 1 hour, 1 day, 1 month, and then doing a prediction for that amount of time. The stream processing is like whenever new data comes, we do a prediction. There are companies that focus entirely on stream prediction. Processing, like B2C companies that interact directly with clients in websites, they need to have stream processing. In our case, we don't need that granularity of prediction, so it's a bit of both, but mostly batch processing. Things like human feedback loops and user experience, also very important. We've been doing some cool experiments with this. So having a model that one of the inputs can be human inputs, not for the prediction, but to retrain and to learn. And we have buttons or pop-ups for the client, the user, to say if that's okay, it's not okay, to give some bit feedback, and then we use that like to to f- to retrain the models. And then we have things like more in the part of the production code of code profiling and testing, which is also very important. So this is more in the development stage, but the code profiling is basically understanding how that code that has been tested and run for 10 turbines will behave and perform for 10,000. And there are actually some cool technologies that can do this very easily, and we need to interpret the results and then like do the fixes to make it run smoothly for 10,000 turbines. And that's it, I think. Yep.